Yeah, so welcome everybody. Cool that you could come. I think Paula has a few things to say, logistic things.
Hi everybody. I'm Paula Lucas. I'm the manager for CCQ, and I just wanted to make sure folks know Diane Loring, who you have been hearing from, is in the back, and Mary Kate, who you might have met when you came in. If you have any questions during your time here, we're around, please feel free to ask. Some logistics, the restrooms are just out and to the right. We'll have some breaks and lunch. At the end of your day today, we're all going to go up to the roof for a little reception. It's really beautiful up there. Hopefully the weather will be lovely and we can hang out up there for a while. And then you guys will move on to a restaurant in the neighborhood called Sarah Beth's. If you probably will just all go together, but if for some reason you need, the address is on your agenda, but if you need more directions or anything, just let one of us know. A couple of logistical things. One thing is you are being recorded. If you're a speaker and you do not want to be recorded, make sure you let us know. But keep in mind, just for comments, questions, conversation, the mics above you are always live. So we will edit what goes on the website eventually, but just keep that in mind. Diane, anything else? Like I said, if you have any questions, please feel free to ask us. We're here to, if you have any concerns about your hotel or any questions about logistics here in New York, please feel free to let us know.
Thanks, Paul.
Great, have a good workshop.
Okay, so I'll chair the first session. So just to say something about the format, we set this over email. The talks are going to be 25 minutes plus 10 minutes of questions. That leaves a little bit of leeway for 27, 28-minute talk. We'll try to cut you off hard at 30 minutes. I'll give a 5-minute warning, which is before the end of the talking time.
So at 20 minutes.
At 20 minutes, yeah. And then hopefully there's enough time for discussion. Okay, so our first speaker then is Barry, and he'll be talking about Weyl-charge density waves.
Hi, so thanks for the introduction, and thanks again for the invitation to what I hope will end up being a very great conference. I'm happy to be the one to kick things off. And this is good because this way you'll suffer through me giving an experimental talk very early, and then we can move on with our lives. So, yeah, I'm going to be talking about some recent experiments that I got to help work on some of the theory for on Weyl-charge density waves. I changed the title a little bit from what's printed because I couldn't pass up the opportunity for alliteration. So I'll tell you about chiral currents and a correlated compound. So just as an overview, I'll start with a quick review of Weyl semimetals and how they emerge in chiral crystals, with a particular focus on this material that we're interested in, tantalum, selenium, iodide. Then we'll talk a little bit about the electrodynamics of charge density waves in general and the classical theory of those phenomena. And then I'll talk about what we expect to change in systems with Weyl fermions, and then go over what was actually seen in the experiments done by Johannes Guth. So just to start off, a Weyl semimetal is a nearly free electron material. It has some band crossings in its Brouillon zone, and each two-band crossing in 3 dimensions in general can be represented as some Hamiltonian that looks like this here. Sigma are the Pauli matrices, and these D's are some functions of the momentum. Now, if I look at this, it's a function. Well, I have 3 functions, each of these DIs, and I have 3 variables, kx, ky, kz, and I want to ask when can the 2 bands touch, which is, to have that happen, each of these 3 functions DI has to be 0. And if I don't have any extra symmetries that place constraints on things, then the set of solutions to the system of 3 equations with 3 variables is some set of 0-dimensional points. And these points are what we call Weyl points. And now the Weyl points are topologically stable. So you can imagine trying to add some terms to this Hamiltonian to gap this twofold degeneracy. But what you find is that you can gap it at one point, but what you've actually just done is shifted it to another point. And the underlying reason for this stability comes from topology. And so what we can do is look at this low energy Hamiltonian. I'll simplify things a little bit and just make all of these linear functions of k. You can always coordinate transform things so it looks roughly like this modulo some constant or some tilting terms. And then I can ask, let's consider some constant energy surface in one of the bands for this Hamiltonian, and I can compute the Berry connection for that set of states and the Berry curvature. And what I find is that this twofold degeneracy acts as a monopole source of Berry curvature. In particular, what that means is if I integrate the curvature over any constant energy surface that encloses this Weyl point, I get an integer. And as you know, integers can't change continuously. So no matter what I do to this Hamiltonian, if I fix my constant energy surface, unless some degeneracy passes through the surface that I fixed, I can't change this integral, and so I can't gap this degeneracy. So an important question to ask is what kinds of materials can have these Weyl points? And how many of these points do we have in any given material? And so there are constraints from topology and symmetry that play a role here. So the first thing is a topological constraint, which is known as the Neilson-Ninomiya theorem, which says that if I take the total charge or total monopole charge or Chern number of Weyl points in the Boron zone and add it together, I better get 0. And so with this constraint, what we know is that Weyl points have to come in pairs of plus charge and minus charge. But symmetries can place extra constraints. If I have inversion symmetry, and if I have a Weyl node of plus charge here, inversion symmetry maps it to a degeneracy down here, which has minus charge, because inversion flips the sign of the topological charge. Time reversal symmetry will do something very similar. It'll take a plus charge node here, but it'll actually map it to a plus charge node at the minus k point. So what we can deduce from this is that if we have both inversion symmetry and time reversal symmetry, then each of these points better have 0 charge, because we'll find that plus some number equals minus some number. So what that means is that we get no Weyl points in non-magnetic centrosymmetric crystals. So if we want to find a Weyl semimetal, we need to either break time reversal symmetry or break inversion symmetry. The second consequence is that if we have time reversal symmetry, because time reversed pairs of Weyl nodes have the same charge and the total charge needs to be 0, in non-magnetic systems, these Weyl points come in multiples of 4. So what are particularly interesting are crystals that have no orientation reversing symmetries other than time reversal symmetries. These are what we're going to call chiral crystals. And what was shown in a paper by Zahid Hassan and in many other works is that if we have such a chiral crystal, then all twofold degeneracies are Weyl points, even the ones that occur at high symmetry points. Okay, so that's sort of a lightning review of Weyl semimetals. Now let's talk about the physics. And for this talk, the one consequence of Weyl semimetals that will be very important is the electromagnetic response. So let's just take some simple case where I have 2 Weyl points in the Boron zone that I've shown project everything down to 1 dimension. And I want to ask, what happens if I apply a magnetic field to this system? So if I apply a magnetic field, these Weyl cones break up into lambda levels, and I have one good momentum index, that's the momentum that is parallel to the magnetic field. And so at each value of momentum, I get some lambda levels. The peculiar feature of these Weyl points is that they all have a 0th lambda level, and that 0th lambda level is chiral and has a velocity that matches in sign to the charge of the Weyl point. So I have 1 plus charge node and 1 minus charge node. Now let's, TV's really bad placed. Now let's turn on an let's put the Fermi level here so that it just sits in this 0th lambda level for both of these Weyl points. And let's turn on an electric field and ask what happens. So electrons have charge, so semi-classically at least, what this electric field is going to do is it's going to cause the momentum of each of these electrons to shift, let's say, to the right. Now, if I have some disorder in the system, this shift isn't going to go on forever, and I'll get some finite depopulation of states here and some increase in population of states here. And then I can ask, what's the net current carried by this new steady state? And I can calculate that by just, all of these states that I've depopulated are moving in one direction, and all of these states that I've added to the population of are moving in the opposite direction. So what that means is that I've generated a current through this process. And that current will be given by, proportional to the difference in these populations. And you can work it through and find that this is proportional to the electric field times the magnetic field. Now this is a manifestation of what in high energy physics is called the chiral or Adler-Beljakiv anomaly. And it's an anomaly because you would expect that the population of electrons in each of these Weyl cones or valleys would be conserved. And what we see is that in the presence of parallel electric and magnetic fields, this is no longer true. In high energy physics, this is sort of esoteric phenomena that comes from the way that you regularize the theory. Here we get a little bit of a simpler explanation because we're working with lattice systems and our theories are already regularized. And the reason that this happens, we can see, is if I complete this picture here, this 0th lambda level from this Weyl cone actually connects at some low energy to the 0th lambda level from the other. And so what I'm doing is pumping these states from one chiralid to the other through these low energy states down here. So this is the case with just 2 Weyl cones. And of course, with just 2 Weyl cones, I don't have any time reversal symmetry. So I can ask what happens if I do add time reversal symmetry. And in that case, under the assumption that scattering between valleys by impurities is very weak, then what I find is that each of these pairs of Weyl nodes gives an independent contribution to this chiral current. Okay, so much for non-interacting systems. Now let's move on to a specific compound, and that's this tantalum selenium iodide. So this compound is in the space group I422, which has number 97. And what one could note about this space group from this symbol is that it has no orientation reversing elements. It has some 4-fold rotations and 2-fold rotations, but no mirror symmetries or inversion symmetries. And so that means that it's one of these chiral crystals that we were talking about just a few minutes ago. And so any 2-fold degeneracy in this system will be expected to be a Weyl point. And so here's a picture of the crystal structure. You can see that there's these long chains of tantalum atoms and then is selenium and iodine. And here's a picture of the band structure as computed in DFT. And you can see the crossing, things look, almost completely gapped, and then we have some bands that cross the gap and meet in 2-fold degeneracies. So these pictures were taken from Topological quantumchemistry.com, and you can see also a paper by Chiang et al. Who have similar comments about this compound.
So it's chiral along the z-axis?
It's along, well, the space group is chiral in the sense that there's no orientation reversing elements. So,
okay.
But yeah, if you want to think about chiral molecules, then what I have is a bunch of chains. And, well, here I didn't put them along Z, but we may as well put them along Z. Okay, so this is, this band structure is, from a condensed matter point of view, almost ideal for a Weyl semimetal. And of course, this is not what's seen in any experiments. So what is seen in experiments is that this compound has an instability, a pyros instability, along these quasi-1D chains. So if I orient things, so I have my tantalum atoms in these chains, what happens is I get a dimerization. And this is driven by the electron-phonon coupling and pairing across electrons that live in different Fermi pockets on this, near these Weyl points. And so you can see these two papers here for some, well, these plots are taken from these two papers. They also comment on the nature of this phase transition. In particular, this recent paper here is relevant for the experiments that I will tell you about. And so we have this pyros instability, and so we can ask in the low temperature phase after the structure distorts, what happens to this nice, beautiful Weyl semimetal that I started with? And if we go back to these classic experiments from 1983, they looked at the resistance of this compound as a function of here 1 over temperature. And what you see in this plot, so the bold line is log of the resistance, the sort of spots are its derivative, and you see that there's this kink at this temperature here. And the kink is even more pronounced in the derivative of the resistance. So this tells you that there's some phase transition at this temperature. And then in the low temperature phase down here, we see exponentially suppressed conduction. So what this tells us is that this kink here is a metal insulator transition. So what's happening is we have this nice Weyl semimetal, we lower the temperature, it undergoes a pyros distortion, and these states near the Fermi surface gap and leave us with an insulator. So this charge density wave insulator still has interesting electrodynamic properties, even if it weren't from a Weyl phase originally. And so I just want to quickly review the properties of the electrodynamics of charge density waves. So in the sort of standard picture for what happens in these materials, I have some Fermi C, and I have my Fermi level here. I have some points K star and K star plus Q at the edge of the Fermi level. And what happens is that because of the coupling between the electrons and phonons, the distortion happens when some finite wave vector phonon mode acquires an expectation value. And so what this means is that the crystal shifts. And at the mean field level, this translates to an expectation value for this pairing operator that destroys an electron at this end of the Fermi pocket and creates an electron at this side of the Fermi pocket. So this is what we'll call the order parameter for this phase. This differs from the conventional definitions by some factors of electron-phonon coupling and Fermi velocity that won't be important for this talk. And so we'll call this delta is the amplitude of this order parameter, and phi is its phase. So if we take some non-interacting Hamiltonian and condense an operator like this, just like in BCS theory, we open up a gap in the spectrum. Except here, instead of condensing particles with charge 2 like Cooper pairs, we're condensing particles with charge 0. We're condensing electron hole pairs, but separated by some momentum. So we can ask what giving this thing an expectation value does. Well, let's look at the density operator for electrons. So the density operator is the sum over K and Q of things that just create an electron at K and destroy an electron at K plus Q. So if I condense this pairing operator like I did, what I do is I create some non-zero wave vector component of my electron density. So if I just take this average, I get my average density, which is what I get when Q is 0, and then I get 2 times the magnitude of my order parameter, and then a cosine, where the wave vector of the cosine is my pairing wave vector from before, and its phase is the phase of my order parameter. So you can see in pictures what happens here in a 1D or quasi-1D system is I start off with some undistorted state. I have my atoms with some lattice spacing A, and I have my Fermi C with my Fermi level, let's say here. And then this phonon mode acquires an average, which means that my system dimerizes. This causes my electron density to also become modulated by this same wave vector, and I open a gap of magnitude delta at the Fermi level. So you can see from this picture that the single particle degrees of freedom in the system are now gapped in the low temperature distorted phase. So we can ask, what is the low energy physics of such a system? Well, if I look at this density, or my order parameter, there's two collective modes that are sitting around. The first is this amplitude mode delta. So delta can fluctuate beyond the mean field theory, and fluctuations change the amplitude of the pairing. And so this mode is actually massive, and so there's some energy gap to fluctuations in delta. Because of that, when we're looking at the low energy physics, we'll ignore the fluctuations of delta and just leave it as some constant. But there's another collective degree of freedom here, which is the phase of the charge density wave. And this is the Goldstone mode for the broken symmetry, which here is the translation symmetry of the system. And so this phi is in principle free to fluctuate and change. And the surprising and rather counterintuitive thing is that when I excite this mode phi and shift my charge density wave, even though my order parameter is some neutral object, fluctuations in phi carry current. So one could and rightly should ask, how can fluctuations of some neutral order parameter carry current? Well, there's two ways that one can look at this. The first is sort of the explanation that Froelich provided. It's interesting to note that Froelich originally presented this theory as his theory of how superconductivity in all compounds works. And we'll see later why this is not the case. But let's think about what's happening here. So phi is simultaneously the phase of two things. It's the phase of my lattice distortion, and it's the phase of my electron density distortion. And so if phi starts to shift, that means my density wave is sliding. And so my electrons are moving and my ions are moving. And so you would think that, well, this would carry no current. Everything's just kind of shifting uniformly. But what Froelich pointed out is that the electrons are free to collectively slide through the crystal over long distances, whereas the ions, even though the phase can shift, each individual ion is only free to oscillate around its equilibrium position. And so what happens in this sliding process is that the electrons actually move coherently, whereas the ions don't, and the electrons conduct currents through the system. There's a semi-classical picture that makes this a little bit more clear, which is, let's take this band structure for the gap phase I showed before and ask what happens if I let this phase of this charge density wave be time dependent. And what happens if I do that in the mean field theory is I sort of shift the momentum of all of my states together. Not just the states in that are occupied below the Fermi sea, though, actually even the unoccupied states. So these gaps shift. So everything has shifted over by this amount proportional to d phi dt, and then I can look at this picture and see that the occupied ground states now carry a current, because if I just sum up the momentum of all of these states, it's no longer zero. And it's proportional to this rate of change of the phase field. So the sliding mode carries current. Froelich thought that this was the origin of supercurrent and everything. Of course, in real materials, the sliding mode is pinned by disorder or incommensuration with the underlying lattice. And you can see this in AC conductivity measurements that were done in the 80s on the same tantalum selenium iodide compound. Instead of seeing an infinite current at zero temperature, or at zero frequency, what you actually see is this sort of Lorentzian profile for the current as a function of frequency that corresponds to a phenomenological equation of motion like this for the sliding field. There's some scattering rate, gamma, that describes scattering off of impurities, so this decreases the amplitude. And then there's some pinning frequency, omega, that tells me that this field is not actually free to slide as much as it wants, but it's pinned to impurities in the crystal. So for low pinning, this gives me, I can solve this and I can find the conductivity as a function of frequency, and I can define some conductivity sigma CDW that I get in the absence of pinning, and it's finite. So how do we overcome pinning? Well, we can just increase the electric field more and more, and at some point we'll have enough energy that things will start to happen. And Bardeen presented a theory for this based off of tunneling. And the idea is, so here I'm going to show a band structure. And this is not the band structure for the electrons in the system. This is actually a band structure that represents the states of oscillations of everything. So because of this gap here is going to be proportional to this pinning frequency that I just showed you. And so I can ask, what's the probability in the presence of an electric field that I tunnel between these two states? And Bradlyn argued that this tunneling came from two contributions. One is just the exponential activated tunneling, from the lower band here to the upper band that's suppressed by some threshold voltage or electric field. And the other thing that he did was to note that there's some coherence length over which the electric field is able to influence the sliding mode of the charge density wave. So it's the coherence length for the sliding mode. And if I look at what happens to bands for this sliding mode in the presence of an electric field, they tilt, and I can only have tunneling across the gap like this. And so Bradlyn argued that the fact that this length is smaller than the total coherence length of the sliding mode would decrease the tunneling probability by this factor, 1 minus the ratio of electric field to the threshold field. And so we expect to see some nonlinear conductance of the sliding mode that looks like this in the presence of disorder or incommensurate.
What are the units of that structure? Can you draw that on the left?
On the left.
This is like space over energy.
Yeah, so this is one of these plots that I would do in semiconductor physics, where I have some electric field, so I make one of these band bending pictures. So the x-axis here is going to be length, and this axis is energy in some appropriate units. Okay, so since I have, I guess, negative time, okay, but then really 6 minutes. Okay. So I'll talk about what do we expect to change in a Weyl system. So if we have Weyl points, then we don't just have pairing between opposite sides of an inert Fermi sea. We can have pairing between fermions that live in one Weyl cone and fermions that live in a Weyl cone of opposite charge. And what Wang and Zhang argued is that if we have broken time reversal symmetry, then the phase of the charge density wave gets tied to an electromagnetic response. And in fact, it gets tied to this electromagnetic theta angle. And the way that they argued this is they considered some mean field theory for Weyl semimetals with electron-phonon coupling that they've integrated, electron-phonon coupling that they've parametrized by this M here. And they did a low energy expansion around the two Weyl cones. And then they said, well, let's integrate things out. And to do this, what we want to do is first do a chiral transformation that moves everything to 1K point. And doing this produces some anomalous term in the action that looks like this. And because this field M acquires, M before was the order parameter for the charge density wave, it acquires a phase. This phase gets carried over into this chiral transformation, and we end up with a change in the action that couples phi, the sliding mode of the charge density wave, to E dot B. If we look at this action and ask what does it do, what does it contribute to the electric current of the system, we can take a variation of it with respect to A, the electromagnetic gauge field, and we find that it contributes in the uniform state of current that's proportional to an applied magnetic field B and the time rate of change of the sliding mode, phi dot. And so this looks a lot like a chiral magnetic effect that we would see in a gapless Weyl system, except here it's due to the sliding mode of the charge density wave. So if we look at this, we would expect then that above threshold, where this phi is allowed to fluctuate, we would expect to see additional contribution to the sliding, this should be J, sorry. Oh no, sorry, this is right. Yeah, an additional contribution to the sliding mode dynamics that come from this magnetic field. So if we put this all together, what we would expect to see is a negative magnetoresistance due to the sliding mode of the charge density wave above the threshold voltage. So I can give sort of a microscopic picture for what might be happening here if we sort of reverse our order of thinking. Let's start with a Weyl semimetal, add a magnetic field, and then introduce the mean field theory for the pairing. So if we start with the Weyl semimetal and the magnetic field, we get a set of bands that looks very much like what I drew earlier with a Fermi level here. And we have these 0th Landau levels, and the degeneracy of each of these is proportional to the magnetic field. Now I introduce or turn back on my pyros instability, and what I find is that I have pairing of electrons in one of these pockets with holes in the other of these pockets. This leads to a gap charge density wave, and in fact this is only a quasi one-dimensional system. Because of the degeneracy of these Landau levels, you can think of it as B different one-dimensional systems where B is the strength of the magnetic field. And so then the sliding mode for each of these B one-dimensional systems will carry a current, and this is responsible for this negative magnetoresistance. So this was all without time reversal symmetry. Let's add time reversal symmetry back in, and then we have, once we project everything down onto one direction, we have what looked like counter-propagating 0th Landau levels. But as long as the intervalley scattering is weak, remember these two Landau levels actually come from vials at different K points. They just get projected onto each other through the magnetic field. As long as the intervalley scattering is weak, we would expect to see an additive conductance from each of these pairs of channels. So the punchline is, we should look for negative magnetoresistance in vial CDWs such as the tantalum, selenium, iodide. And so that's what Johannes did. He took the samples, the crystals look like this. They're very long and thin. He prepared them as such with some contacts where he injected a current between 1 and 4 and measured the voltage between 2 and 3. Just looking at linear transport, we see very well reproduced this experimental phase resistivity plot I showed before, where you can identify the phase transition. We can look at pinning of the sliding mode. So we see that below the transition temperature, there is some threshold voltage that we need to apply to get any current to flow. Apologies to John Bardeen for the fact that his name is misspelled in the figures. If things were ohmic, we would expect just this linear IV curve, and instead we see this activation. And we can actually fit these plots to Bardeen's tunneling theory in zero field, and what we find is that the conduction due to the sliding mode is very well described by this Bardeen tunneling theory. So now let's turn on a magnetic field and see what happens. And, well, here's the punchline. So I'll leave this up since Jen is giving me the sign I'm out of time. You can look at the change in dI/dV as a function of magnetic field. And what we see is these nice parabolas reminiscent of semimetals, except here we're in the sliding regime of this charge density wave compound. And we can look at the angle dependence, the dependence on this conduction between the angle between E and B, and we see that it's maybe not quite cosine squared phi, but it's certainly modulated and has a strong harmonic contribution from that term. So I'll conclude with that, and thanks to, well, of course, the organizers and all of my collaborators on this paper, especially Johannes, who did these amazing experiments. So thanks.
Is it important what the direction of the magnetic field is with respect to the Q vector of the charge density wave?
So what is important is that, well, there's two things that are important. The direction between E and B, and if you want to activate the sliding mode of the charge density wave, then you need to have a component of E parallel, so the Q vector.
How much does it matter that the CDW is like a truly 3D kind of thing, since that there's like some many vectors and a lattice kind of thing, lattice-ish modulation? So
for the specific experiment, not much, because the samples are not, the samples of themselves are quasi one-dimensional.
Is that a sample statement or a crystal, like a unit cell geometry statement?
I would suspect it's a unit cell geometry statement.
What's the general expectations of magnetic field on sliding CDW without all this Weyl physics?
Without all this biophysics, if there is no residual single particle density of states in the charge density wave state, then the magnetic field is expected to not contribute.
So do nothing.
Right.
Expect zero magnetic resistance.
Yes.
Sliding CDW.
So there are experiments on some other charge density waves, such as, actually I forget the compound, but I can get back to you on it, where there is a residual Fermi pocket even after you, so you open this charge gap, and there's still some residual density of state somewhere else in the boron zone, and there is magneto resistance seen. But in truly gapped CDWs, there's usually zero magneto resistance.
You had it as a question at the end, like, do you understand what happens to the surface states when you gap this, like with the CDW? Because in this theory of the charge density wave, like if you break down Versa, you're allowed to add terms at the surface that might change stuff. And if you have time reversal, if the vials are not of the same energy, so then you can, first of all, connect differently.
Right. So the role of the, so I can say two things. First, the role of the surface states in our experiment, we can't really probe them because of the sample geometry and the way we applied the contacts. So I don't have any intuition for what would happen, which is why I agree with you. It's an interesting question for future work.
In the presence of time reversal symmetry, if you have, say, many pairs of Weyl points in the brilliant zone, is it clear that the coupling phi E dot B is the same for all pairs of Weyl points? That it doesn't change sign. Say for a pair is plus phi E dot B and the other one is minus phi.
It's not clear, but for the magneto resistance, this isn't important. So the sign of the coupling is important for the anomalous Hall effect. And this is why you get zero anomalous Hall conductivity.
Okay.
But for the magneto resistance, what happens is, the sign isn't so important. What's important is that you have a conducting channel.
Yeah, it has been studied in the past that an applied magnetic field can actually act something like a pair breaking, like in a superconductor in CDW. So I guess that's not irrelevant in this case.
It's not irrelevant. So when we did the fits for the magneto resistance, we don't just fit to this B squared. It's really a fit to this sigma CDW times B squared plus single particle contributions. And so we extract the single particle contributions.
Yeah. So since it's pyros, so there are actually two kind of Weyl point, right? So they have different Q. Like a different Q for the charge density wave, I guess.
In principle, one could consider a case like that. So what we've so actually you can see. Let me put the reference back up. So in this paper here, and actually in this plot here, they analyze all of the different Q vectors that contribute to the CDW in this compound.
So another quick question is that since the Weyl point is gapped by the CW, so why the inter-valley scattering is still weak? Because now it's kind of coupled by the CW, right?
Right. So now what inter-valley scattering in this picture means is sort of So if we draw this picture where we have a bunch of different Weyl points, you can imagine pairing amplitudes between all of the pockets. And what I really mean is that scattering between the different pairing states is weak. So that if I have pairing here and here, I don't have scattering of the sliding mode in one pocket to the sliding mode.
In this other compound that you mentioned, that they see magneto resistance, is positive or negative?
believe it was positive, and it was also not, well, I don't know if they looked at the angle dependence, but it wouldn't be angle dependent in the same way.
Just naively, so when you gap them, I guess you could have trivial or TI or topological insulators. So probably the results of gapless bands still around. But is it trying to be a topological insulator or a trivial insulator like gapping?
So this sort of goes back to this question on surface states here. And so this is why this would be an interesting thing to look at. I mean, really what happens is it's trying to be something in between the two. And so what you start with in the Weyl phase is a bunch of Fermi arc surface states. And then you gap it with the CDW. And I think it's an interesting question to ask what happens to the Fermi arc surface states in the system.
It's got 48 nodes, so 48 divided by 4 is still even.
Maybe one quick comment. So for the surface state, if you look at surface state away from your Fermi surface, then that should not be influenced by your charge density wave pairing. Because charge density pairing is much smaller than the end scale of the Fermi energy. And then, so as a white node, or you?
So the thing about the Weyl surface states though is we know that we can't forget about what's happening near the projection of the Weyl points, because these Fermi arc surface states actually start to delocalize into the bulk. And
away you still get the surface Fermi arcs.
Right, but the question is what happens near, and how do we how do we complete the Fermi contour?
Yeah, I remember that for Weyls, the negative millimeter resistance was also predicted to be like a signature of this Carter anomaly. And then there was this big debate whether the experimental evidence is really due to that or due to some geometric effects.
I have a slide.
Yes.
Good, now I get to talk about the slide. So, one thing, as Niels pointed out, that's important to do is exclude extrinsic contributions to magnetoresistance, such as current jetting, which comes from inhomogeneities in the current profile. And so what we, and really Johannes did to exclude this, is we can consider a sample now with 6 contacts instead of just 4, where we still have 2 current injection contacts at the ends of the sample. And then we can look at the resistance or conductivity with contacts that are on one side of the sample versus contacts that are on the other side of the sample. And we can compare these two things to look for signatures of inhomogeneities in the flow profile. And what we find is remarkable consistency between the two. So we can conclude from this that inhomogeneities in the flow are not important, or not influencing our negative magnetoresistance.
Okay, I want to move on. So let's thank Barry again.